Principal component analysis, or PCA, is like a data scientist's magic wand for cutting through the noise. Imagine you have a giant spreadsheet with dozens of columns. Maybe it's customer data with age, income, purchase history, and so on. Trying to make sense of all that at once is overwhelming. PCA steps in to simplify things. At its core, PCA is a technique that takes your complex, high-dimensional data and compresses it into just a few key components without losing the big picture. It's like summarizing a 500-page book into a short summary that still captures the main ideas. Why does this matter? Because simpler data is easier to visualize, faster to analyze, and more efficient for machine learning. Instead of wrestling with endless columns, PCA helps you focus on what truly drives the patterns in your data. So whether you're working with financial records, genetics, or even image recognition, PCA is a tool that turns chaos into clarity. Principal component analysis is essentially a data simplification tool. Think of it like packing for a trip. Instead of hauling your entire closet, you select just the few most versatile outfits that cover all your needs. PCA does something similar with your data. It takes all those complicated variables in your dataset and identifies the most important combinations, called principal components. These new components capture the essence of your data using far fewer dimensions. For example, if you had 100 measurements about car performance, PCA might reduce this to just 2 to 3 key indicators that still show the main differences between vehicles. This technique shines in 3 main areas. First, for visualizing complex data in 2D or 3D plots. Second, for cleaning up noisy data by focusing on the meaningful patterns. And third, as a crucial pre-processing step in machine learning to make algorithms run faster and more efficiently. The math behind it is elegant, but don't worry, you don't need to understand matrix algebra to use PCA effectively. Let's talk about why PCA is such a game changer in data science. First, it acts like a smart filter for your data. Many datasets contain redundant or overlapping variables. PCA identifies and removes these, keeping only what's truly meaningful. Second, it's a speed booster for machine learning. By reducing the number of features, PCA cuts down training time dramatically. Imagine running a race with a lighter backpack. Third, it unlocks the power of visualization. High-dimensional data is impossible to plot, but PCA lets us see patterns in 2D or 3D, turning abstract numbers into something we can actually explore. Finally, it's efficient. Smaller datasets mean less storage space and faster processing, saving both time and resources. Whether you're working with financial forecasts, medical imaging, or customer analytics, PCA helps you work smarter, not harder. To really understand how PCA works, we need to grasp 2 fundamental ideas: variance and covariance. Let me explain them simply. Variance is like measuring how spread out your data is. Imagine a group of friends at a park. If they're all standing close together, that's low variance. But if they're scattered far apart, that's high variance. PCA loves high variance because it means there's meaningful information to work with. Now, covariance is about relationships. If 2 variables, like height and weight, tend to increase together, they have positive covariance. If one goes up while the other goes down, that's negative covariance. And if they don't affect each other at all, covariance is 0. Here's the magic. PCA uses these concepts to find the directions where your data has maximum variance. These become your principal components. It's like finding the best angles to view your data so you see the most interesting patterns. The first principal component captures the most variance, the second captures the next most, and so on. Don't worry about the math for now. Just remember, PCA is essentially a smart way to identify and rank the most important patterns in your data based on how spread out and interrelated your variables are. Let's walk through exactly how PCA transforms your data. Think of this like following a recipe. We'll go through each step carefully. First, we standardize the data. This means adjusting all variables to the same scale so that one feature doesn't dominate just because it happens to have larger numbers. It's like giving every player in a game the same starting point. Next, we calculate the covariance matrix. This shows us how all our variables relate to each other. which ones move together and which move in opposite directions. Imagine this as creating a relationship map of your data features. Then comes the math magic. We compute the eigenvalues and eigenvectors. These tell us the key directions where our data varies the most, eigenvectors, and how much variance each direction accounts for, eigenvalues. Picture finding the natural axis of your data's shape. Now we select the most important principal components. We pick the eigenvectors with the largest eigenvalues. These are the directions that matter most. It's like choosing only the loudest voices in a crowd to listen to. Finally, we transform our data by projecting it onto these new principal components. This gives us a simplified version of our dataset with fewer dimensions, but all the key information intact. The result? Your complex data is now cleaner, more compact, and ready for analysis or machine learning, all while keeping what truly matters. Let's break down two of the most important, but often intimidating, concepts in PCA, eigenvectors and eigenvalues. Don't worry, they're simpler than they sound. Imagine you're looking at a stretched out cloud of data points. Eigenvectors are simply the natural directions where your data stretches the most. Think of them like the grain in a piece of wood. They show you the natural lines along which your data wants to flow. In PCA, these become your new, more meaningful axes. Now, eigenvalues tell you how important each of these directions is. A big eigenvalue means that direction accounts for lots of variation in your data, while a small one means it's less significant. It's like rating each eigenvector on a scale of how much information it holds. Here's the key. PCA uses these to rank your components. The eigenvector with the largest eigenvalue becomes your first principal component, the single most important direction in your data. The next biggest gives you your second component, and so on. This elegant system automatically sorts your data's most important patterns for you, which is why PCA is so powerful for simplifying complex datasets while keeping what matters most. Selecting the optimal number of principal components is like packing for a trip. You want enough to be prepared, but not so much that you're weighed down. Here's how to strike that balance. The scree plot is your best friend here. It plots eigenvalues in descending order, showing how much variance each component captures. Look for the elbow, the point where adding more components gives diminishing returns. Think of it like turning up the volume on a speaker. Past a certain point, louder doesn't mean clearer. A common rule of thumb is to keep enough components to explain your 95% of the total variance. This preserves most of the data's structure while dramatically simplifying it. For example, if 5 components cover 95% of your data story, you might safely ignore the remaining 15. Why does this matter? Too few components lose critical details, while too many defeat PCA's purpose of simplification. It's a Goldilocks problem, and tools like the scree plot help you find just right. PCA isn't just theory, it's working behind the scenes in some fascinating real-world applications. Let me show you where this powerful technique makes a difference. In face recognition, PCA helps create eigenfaces, a clever way to represent faces using just a handful of key features rather than thousands of pixels. This makes facial identification systems both faster and more accurate. Genetic researchers rely on PCA to make sense of complex gene expression data. It helps them spot meaningful patterns in DNA while filtering out biological noise, like turning a chaotic radio signal into clear music. Financial analysts use PCA to uncover hidden risk factors in markets. It can reveal the underlying forces that drive stock movements, helping investors make smarter decisions in turbulent markets. And when you send photos online, PCA might be helping compress them. By keeping only the most visually important information, it reduces file sizes dramatically while maintaining picture quality, meaning faster uploads and downloads. From unlocking your phone with your face to helping doctors understand diseases, PCA is quietly powering innovations all around us. It's a perfect example of how abstract math transforms into real-world solutions. PCA comes with both advantages and limitations that are important to understand. Let's look at both sides. On the plus side, PCA is incredibly effective at reducing overfitting in machine learning models. By stripping away unnecessary complexity, it helps models perform better on new, unseen data. It also solves one of the biggest headaches in data science: visualization of high-dimensional data. PCA gives us the superpower to plot and explore data that would otherwise be impossible to visualize. Another major benefit is how it handles correlated features. Instead of struggling with redundant variables, PCA combines them into clean, independent components that capture the essential information. But there are trade-offs. The transformed components can be tricky to interpret since they're mathematical combinations of original features. You lose the straightforward meaning of individual variables. PCA is also sensitive to how we scale our data. Without proper normalization, variables with larger ranges can dominate the components even if they're not actually more important. The key is knowing when these trade-offs are worth it. For exploratory analysis and preprocessing, PCA's benefits often outweigh its limitations, but it's not always the right solution for every problem. Let's take a quick look back at what we've learned about PCA. At its core, principal component analysis is like a data magician. It takes complex high-dimensional datasets and transforms them into simpler versions without losing the key insights. Whether you're trying to visualize patterns, speed up machine learning models, or clean up noisy data, PCA is a powerful tool to have in your toolkit. To recap, PCA helps you focus on what truly matters in your data by reducing dimensions, improving efficiency, and revealing hidden structures. It's used everywhere from facial recognition to finance, making it one of the most versatile techniques in data science. That's a wrap on our PCA journey. If you have any questions, maybe about how to apply PCA to your own projects or about the math behind it, feel free to drop them in the comments. You don't have to like, you don't have to comment, and you definitely don't have to subscribe. I just want you to watch and walk away with knowledge that actually helps you.